Good evening, everybody. Tom Barlow, professor for Physics 215. It's the calculus-based physics at Northampton County Community College. It's also called Physics for Scientists and Engineers. Some people also call it calc-based physics. Tonight, we're going to be doing Chapter 11. Chapter 11 in the text kind of continues on with the concept of rotation and rotational motion, and we're going to be talking about angular momentum. Now, just 2 chapters ago, we dealt with linear momentum. Now we're going to be talking about angular momentum and general rotation. I'm going to work from the PowerPoint. And what I'm going to do is I'm going to start sharing my screen here. So Chapter 11 deals with angular momentum and general rotation. So this is a picture of a figure skater doing a spin. So we've all seen this in the Olympics and in other things. As this skater is spinning around, sometimes they will move their arms outward and inward. And as you see, when her arms are out wide horizontally, she spins slower. But as she tucks herself in with her arms and legs, she starts spinning much faster. And that has to do with rotational motion and angular momentum. Okay. So just like linear momentum, angular momentum is also conserved. Okay. So in the chapter, we're going to talk about angular momentum, objects rotating about a fixed axis. We're also going to talk about vector cross product, torque as a vector, angular momentum of a particle, angular momentum and torque for a system of particles or general motion, angular momentum and torque for a rigid object, conservation of angular momentum, spinning tops and gyroscopes, rotating reference frames, inertial forces, and something called the Coriolis effect. So for rotation, linear momentum is given by the variable uppercase L. So L is equal to your moment of inertia times your angular velocity. Okay. So L, uppercase L, is angular momentum, moment of inertia times angular velocity. So then Newton's second law, sum of torques can be described as change in linear momentum, change in angular momentum with respect to time. So this form of Newton's second law works even if the moment of inertia is not constant. Okay, so if there are no external torques observed on an object, angular momentum is conserved. So if nothing is acting on it from the outside, angular momentum will be conserved. So change in angular momentum with respect to time is going to be equal to 0. That would mean that angular momentum, which is equal to moment of inertia times angular velocity, is going to be constant. So in definition form, total angular momentum of a rotating object remains constant if the net external torques acting on it is 0. So this means that angular momentum is going to be constant. Therefore, if an object's moment of inertia changes, its angular speed is going to change as well. So like we said, when the swimmer's arms are out wider, relatively speaking, the angular velocity is going to be smaller than if the skater tucks their arms in, they're going to start spinning faster and faster. Same thing with a diver. when they first jump off the board, their rotation about their center of mass, their rotation is going to be slower until they're tucked in into a tight ball, and then it'll slow down slightly as they open back up again. So let's take a look at a pretty simple example. You have an object rotating on a string that is spinning around, and we have a small little hole cut in the center of a table. So you have a small mass M attached to the end of a string, which is rotating in a circle. We're going to ignore friction. We're going to say it's on a frictionless tabletop. The other end of the string passes through a hole in the middle of the table. Initially, the mass revolves with a speed, linear speed of 2.4 meters per second in a circle with radius of 0.1 meters. The string then is slowly pulled through the hole towards the center until it has a radius of 0.48 meters. What is the speed at that location of the mass now? Okay, so I'm going to switch to a whiteboard to work on this. So we're going to use the concept of conservation of linear momentum. So L1 is equal to L2. You could say L initial is equal to L final, however you want to look at it. And we know that angular momentum is moment of inertia times angular velocity at 1, moment of inertia 2, angular velocity at 2. So we're saying we're going to treat this little mass just as if it were like a small particle. Okay. So moment of inertia for a small particle is mr squared. So m r1 squared, angular velocity 1 squared, is equal to mass radius 2 squared and its angular velocity squared. Well, we've got the mass isn't changing from one end to the other. And we really want to know its angular velocity at 0.48, which is this second condition. So angular velocity, I'm just solving what's up here. So it would be W1 times R1 squared divided by R2 squared. Okay, and we know what's going to help us here a little bit is our linear velocity is going to be equal to R times angular velocity. So if we want to know this, I can take this value here and substitute this in. So my linear velocity at 2 is going to be my radius at 2 times this whole thing. Angular velocity at 1, radius 1 squared divided by radius 2 squared. Well, that's handy. One of these radii will cancel. Right? One of the radii will cancel, and I also have V1, R1. If I have a V1 and an R1, that's going to just be a V. So I'm going to do another substitution, and then I'm going to drop one of these R's and this R squared. So V1, R1, or V1, R1 squared is going to be V1 times R1, because one of these R's, one of these R1s is going to this V1, divided by R2. So that simplifies pretty nicely. We're given that the velocity when it's out at the edge of the table is 2.4 meters per second. That was given to us in the problem. The length of the string at point 1 or position 1 is 0.8 meters. The length of the string at position 2 is 0.48 meters. And velocity 2 is going to be roughly 4 meters per second. So you don't have to solve the algebra this way. You can plug the numbers in at any given point in time, and you don't have to do the simplifications with the R's. You can keep the equations as they are and solve them that way. Back to the PowerPoint. So we solve that. Our velocity, when we pull the string in, we expect it to go up because you're pulling it in tighter, 4 meters per second. Okay. So now we're going to do another example. We're going to take a look at something called a clutch. A clutch consists of two cylindrical plates, plate A and plate B, that you see here. Here's plate A, here's plate B. They're going to be pressed together until they come in contact with each other. So they're on two axles, and they're the two plates have, plate A has a mass of 6 kilograms, plate B has a mass of 9 kilograms. They both have the same radius, 0.6 meters, and they are initially separated by some distance. Plate A is accelerated from rest to an angular velocity of 7.2 radians per second in a 2-second time span. So part A, they want us to solve the angular momentum of plate A. Part B, they want us to solve the torque required to have accelerated the plate from rest to the 7.2 radians per second. And then they want us to, plate B is initially at rest, but is free to rotate, so it's not held. And then you take plate A, which is rotating, and it will come into firm contact with plate B, and the two plates will then rotate at some constant angular velocity after they come into contact with one another. So it's going to be less than the initial angular velocity of 7.2 that A has. So they want to know, why does it happen? Well, why it happens is we know already why it happens, that angular momentum is going to be conserved. If plate A is spinning initially, plate B is sitting at rest, they come into contact with one another. It's kind of like the train cars colliding linearly. You're going to expect it to go down. And then they want us to figure out that speed after they've come into contact with one another. So I'm going to go from PowerPoint back over to a whiteboard. All right. Part A. Part A, linear momentum. okay? I'm sorry, the angular momentum. They want us to find angular momentum of A. Angular momentum of A is L of A is equal to the moment of inertia of A times angular velocity. Well, the moment of inertia of this plate comes from the table in the previous chapter. That is equal to 1/2 ma r sub 0 theta. Okay. So if I plug this in over here, it's going to be 1/2 ma r sub 0 theta times W1, or angular velocity 1. So 1/2 times plate A was given to us as 6 kilograms. Our radius is 0.60 for both plates. That's meters, so that's squared. So this is going to be my moment of inertia. Now you could have calculated the moment of inertia and then plugged in, or you can plug the numbers in right here at the end. Angular velocity was given to us at 7.9 radians per second. So our angular momentum, 7.8 kilogram meter squared per second. So this is part A. Part B, they want us to determine the torque required to have accelerated that plate from rest to the 7.2 radians. So torque can be given as change in angular momentum with respect to time. The angular momentum initially is going to be 0 because it started from rest, right? There's no velocity, no angular velocity, so that term would be 0. So it is just going to be my final angular momentum, which we solved for in the first part. And it was accelerated over a time of 2 seconds. So our torque, part B, the torque required to do this acceleration is 3.9 Newton meters. Okay. Part C, I am going to clear the screen because I need more room to do this one, okay? So this is part C, same problem, part C. So we're looking at angular momentum before the collision, before the two plates come into contact with one another, and angular momentum after. So before, you have moment of inertia of plate A times the angular velocity of plate A. In the final condition, plate A and plate B have come into contact with one another. So you have to add their moments of inertia. But at that point, they're both going to be rotating with the same angular velocity. Okay. So if I solve this for W2, or angular velocity after they've come into contact with one another, I am going to end up with A divided by the moment of inertia, A plus B, so this divided by this times that. Okay. So if I look at this, right, your moment of inertia is equal to 1/2 MA RO squared. Okay. W2 is equal to 1/2 MA RO squared divided by quantity of 1/2 MA RO squared RO squared plus 1/2 MB RO squared. So you can see that I can factor out this 1/2 and this RO squared and bring it out. And then I have this 1/2 and RO squared. So all of this cancels so that it reduces down to MA over MA plus MB. Now, there's nothing wrong. You're given the masses and the radiuses. There's nothing wrong with solving for your moments of inertia for each one and plugging those in. This is just, one method to go through and reduce the amount of algebra and calculations that you're doing, but it will work either way. So we're given that MA is 6 kilograms. MB has the same radius, but it's 9 kilograms. So 6 kilograms plus 9 kilograms. And then this whole thing is multiplied by what we were given, the 7.2 radians per second. So angular velocity after the collision is 2.9 radians per second, which you would expect because initially it was the 7.2. And the second one is at rest, so now they're both rotating at 2.9 radians per second after they've come into contact. Okay. So, and again, the reason that the speed, so why does it happen? Angular momentum's conserved. So that's the reason why. I'm going to do another example. You have a neutron star. An astronomer detects stars that are rotating extremely rapidly, known as neutron stars. A neutron star is believed to form from the inner core of a larger star that has collapsed under its own gravitation to a star of a very small size but a very high density. Before the collapse, let's assume that the core of such a star is the size of our sun, 7 times 10 to the 5th kilometers, and has a mass 2 times as great as our sun. Okay, so the mass is double that of our sun and is rotating at a frequency of 1 revolution every 100 days. If it were to undergo gravitational collapse to a neutron star that only has a radius of 10 kilometers, what would its rotation frequency be? Assume the star is a uniform sphere at all times and does not lose mass. Okay. Let's go back to our whiteboard. I'm going to clear. I'm going to basically end up with what I ended up with before. This is an angular momentum problem. L1 is equal to L2. Moment of inertia of 1. Angular velocity at 1 is equal to moment of inertia 2. Angular velocity at 2. Okay. So for a sphere, moment of inertia of a sphere is 2/5 m1 r1 squared. Okay. So I'm going to solve for W2, or angular velocity 2. And I'm going to end up with 2/5 m1 r1 squared divided by 2/5 m2 r2 squared right? So basically what this reduces to is r1 squared divided by r2 squared angular velocity at 1. We know that frequency is angular velocity divided by 2 pi. So we have r1 squared, r2 squared, f1 so this 7 times 10 to the 5th kilometers divided by 10 kilometers, numerator squared, denominator squared. We know that 1 revolution happens every 100 days. But we need to convert this 100 days. There's 24 hours per day. 24. And there's 3,600 seconds every hour. So the rotation rate would be about 600 revolutions every second is what this thing spins at. Angular momentum is a vector for a symmetrical object rotating about a symmetry axis. It is in the same direction as angular velocity. So if you have a person walking along a circular platform, both of them are initially going to be at rest. If the person starts walking along at some speed v, the platform, assumed to be mounted on like a frictionless bearing, will rotate in the opposite direction such that the total angular momentum remains zero. Okay. So if you have a person running on a circular platform, suppose a 60-kilogram person stands at the edge of a 6-meter diameter circular platform, which is mounted on a frictionless bearing, just like the picture that we had, and has a moment of inertia that they gave to us of 1,800 kilogram per meter squared. The platform is initially at rest, but when the person begins running at a speed of 4.2 meters per second with respect to the Earth around its edge, the platform begins to rotate in the opposite direction. They want us to calculate the angular velocity of the platform. So what I'm going to have to do is I'm going to have to switch over here to whiteboard to solve the problem. Okay, so some things before we get started on the solution. We know that angular momentum is moment of inertia multiplied by angular velocity. We also know that moment of inertia for a particle is going to be equal to mr squared. And we also know that if we solve for angular velocity, it is equal to v over r. Or linear velocity is equal to angular velocity times radius, or radius times angular velocity. We saw all that before. Now, if I take this for I, plug it in here, and I take this for angular velocity and plug it in there, I will end up with L is equal to m r squared v over r. Okay. So now total angular momentum is going to be equal to the angular momentum of this person plus the angular momentum of the platform. Total momentum is going to be zero because the platform isn't really going to be moved. Them together, the person and the platform, aren't going to be moving. So if you have m r squared v over r, this is where I got this from. So I'm just plugging it in there. Now the platform, I'm just going to do IW for the platform. All right. Now, rearranging and solving, like I can ditch one of these, right? And I can rearrange this to solve for this angular velocity of the platform. I would end up with m r, because one of them cancels because of the one in the denominator, linear velocity over I. Well, they gave us the I of the platform. Otherwise, we would just get the moment of inertia for a disk and do the substitution, that equation is in that table in the previous chapter. But we know that the person weighs 60 kilograms, the radius is 3 meters. We're given the 4.2 meters per second, and we're given the 1,800 kilogram meter squared. So angular velocity is 0.42 radians per second. And the problem asks, calculate the angular velocity of the platform. There's the angular velocity of the platform. Let's say I asked for revolutions per second. Well, frequency is angular velocity divided by 2 pi. So it would be 0.42 divided by 2 pi. So our frequency would be 0.067 revolutions per second. Period is equal to 1 over frequency. If you do 1 over 0.067, you end up with roughly a period of 15 seconds per revolution. Okay. Go back over to the PowerPoint here. And if we look at a conceptual example, let's say, we have this equipment in the lab, but I'm not in the lab, so I'm just going to describe what happens. Okay, let's say we have this spinning bicycle wheel that has the 2 axes, and I stand on a stationary turntable. And we're going to assume the turntable is frictionless. What would happen if I took that wheel that's spinning one direction? So in this case, looking down on the top of it, it would be spinning counterclockwise. If I suddenly flip it over so that the wheel starts spinning in the opposite direction, what would happen to me on the platform? Well, what would happen to me on the platform is that I would start spinning in the direction that the wheel was originally spinning, but probably quite a bit slower, or at least slower, right? So if you've had Calc 3, this is going to be somewhat boring. Or at the very least, it will end up being a little bit of a review. So you have the vector cross product. So if we look at torque as a vector, it has magnitude and direction. So if you do vector product or vector cross product, so C is going to be vector A crossed with vector B. So in a very simple example, if you take your right hand, again, right hand rule, and you start out at vector A, and you rotate your hand over towards vector B, with your thumb being that axis of rotation that you're spinning about, right? The direction for the cross product is going to be what direction your thumb is pointed as you move from vector A crossed through to vector B, okay? As you see down there in the picture. The equation for this, the cross product, can be written in determinant form. So if you have A crossed with B, here's your first vector on the top, your second vector on the bottom, and you write them out in IJK notation. The determinant for this, if you look, A, Y, B, Z. So for A, or for I, I'm sorry, if you cover up I, so if you cover up this column, you're left with AY crossed with BZ minus AZ crossed with BY. Then for J, if you put your hand over J, you're going to have AZ crossed with BX minus AX crossed with BZ. Right? For K, if you cover up column K, you're going to end up with AX crossed with BY minus AY crossed with BX. And then all you do is, work that math out, to get, the solution. So some other cross product or properties of cross product, if you take A and cross it with A, you're going to end up with 0. Any vector crossed with any vector is going to be 0. A crossed with B is going to be equal to the negative of B crossed with A. And this is distribution, and then these are the derivatives. Okay. Torque can be defined as the vector product of the force and the vector from the point of action of the force to the axis of rotation. Okay. So you have some torque is equal to R, the radius as a vector, times the force as a vector. For a particle, the torque can be defined around some point O. So torque is defined as R crossed with F. So here, R is a positive vector from the particle relative to the origin point O. So let's do an example of this. So what does it mean? Okay, so you have this torque vector. Suppose the vector R is in the XZ plane and is given by R is equal to 1.2 I plus 1.2 K. Calculate the torque vector T if the force is 150 newtons in the eye. Okay. Let's switch over to the whiteboard. So torque is equal to R, the radius, lever arm, crossed with some force. And we're given R and F. So if this is my R and this is my F, and I have I, J, and K, I have 1.2 meters in the I. I have 0 meters in the J, and I have positive 1.2 meters in the K. And then for the force was given to us as just 150 newtons in the I, but 0 in the J and 0 in the K. So now we're going to do that multiplication and addition subtraction based on the equation that we were given 2 slides ago. So for I, you're going to cover up I, and it's 0 crossed with 0, 0 crossed with 1.2. So for I, following that setup, it's going to be 0I plus, you end up with 180 Newton meters in the J, and then you end up with 0 in the K. So it's 180 newtons per meter in the J or in the Y direction. If you want it resolved into one force, you just use the equation the way it was given in the slide. Angular momentum of a particle about a specific axis is given by L is the angular momentum, R is some distance out from some origin point, and P is momentum, right? Is linear momentum. So linear momentum and angular momentum, if you have linear momentum is the change of linear momentum P is related to the net sum of forces, right? And you have change of angular momentum L, right, is related to the net sum of torques. So L is equal to R crossed with P, or RP sine theta. Okay. If we take the derivative of L, we find that the change in linear momentum with respect to time is equal to R crossed with the change in linear momentum with respect to time, right? So if you have R crossed with sum of forces is change in linear momentum with respect to time. And we see that this is equal to change in angular momentum with respect to time. So we have that the sum of net torques is equal to the change in angular momentum with respect to time. So what is the angular momentum of a particle of mass m moving with some horizontal speed, linear speed v, okay, in a circle of radius r in a counterclockwise direction? Okay, well, remember that picture. Go to our whiteboard and I clear this, right? They gave us this picture. You have some center point O, a radius, which is given by a vector. And then you have linear momentum is equal to mass times linear velocity. We know that L is equal to R crossed with P. P is equal to mass times velocity. So now if we plug this in, you have linear or angular momentum is equal to R mass times velocity. We know velocity is equal to angular acceleration times R. So if I plug that in for this V, I end up with R squared m times angular velocity. Well, R squared m is L, angular momentum, is equal to I, moment of inertia, times angular velocity. Angular momentum and torque for a system of particles of general motion. So angular momentum of a system of particles can change only if there is some external torque or torques due to internal forces cancel. So change in angular momentum with respect to time is equal to the sum of external torques. So this equation is valid in any inertial reference frame. It is also valid for the center of mass, even if it's accelerating. So change in angular momentum about some center of mass with respect to time is equal to the sum of torques about that same center of mass. Okay. So for some rigid object, we can show that its angular momentum when rotating around a particle or rotating around a particular axis is given by linear momentum, L, is equal to moment of inertia times angular velocity. Okay. So an elevator is an example of something called a simple Atwood machine. So an Atwood machine consists of two masses, MA and MB. In an elevator, it's the car and a counterweight, which are connected by some cord that has a negligible mass that passes over a pulley. The pulley has a radius of r and has a moment of inertia I about its axle. Determine the acceleration of masses MA and MB and compare to the situation where the moment of inertia of the pulley is ignored. Okay. Switch over to my whiteboard. Clear this. So we know that the pulley has some sort of angular momentum. And we know that torque is equal to the change in angular momentum with respect to time. We know angular momentum is given by moment of inertia times angular velocity. And we know angular velocity is linear velocity divided by radius. So the angular momentum for mass A is linear momentum of A is equal to radius, mass A, velocity. So for B, the angular momentum of B is equal to the same radius, mass of B, times its linear velocity. So total for the whole system, you have MA plus MB velocity times R plus the moment of inertia times V over R. So V over R, here's my moment of inertia, right? Angular velocity is V over R. So now your sum of torques is going to be equal to MA GR minus MA GR, or I'm sorry, this is MB GR minus MA GR. And then from this, torque is equal to change in angular momentum with respect to time. We end up with MB minus MA times GR is equal to MA plus MB times R dV dt plus 1 over R dv dt. And we know that acceleration is dv dt. So the acceleration for that simple Atwood machine. Now, this is without, this is with moment of inertia. MB minus MA, that quantity times G, divided by MA plus MB plus I over R squared. It's an equation. You're allowed an equation sheet for the exam. I would highly recommend having that equation for the exam and also having this equation for the exam. So another equation, acceleration MB minus MA, again, the whole thing times G, divided by MA plus MB. Now, this equation here for A, this ignores moment of inertia. Okay. So the pulley will slow down the system, right? This ignores it, this accounts for it. Okay. Two useful equations to have for the exam. Let's take a look at another conceptual example. If you're holding the same spinning wheel that I was looking at when the professor was on a turntable, but now you're just holding it and you're spinning, so the rotation axis for the spinning wheel, you're holding it with your right hand, okay? The tire is rotating. If you're looking at it, right? If you're looking at it, it is rotating clockwise. It's spinning, and all of a sudden, suppose you're holding this wheel and it's spinning rapidly. Now you suddenly try and tilt it upwards. You suddenly try and lift upwards on it to create, an upward motion in that Z direction. You would kind of expect the wheel to go up if the wheel wasn't rotating, but that wheel is rotating. So if you try and lift it up, what's going to happen is it's going to swerve to the right instead of going up. Well, why does that happen? Okay. So instead, it's going to swerve to the right side. What you're trying to do is you're trying to change the angular moment vector in its direction, not its magnitude, right? So if you remember right-hand rule, it requires that the torque points to the right, which if you create that upward force, you're forcing that right ways movement, okay? So even though you're going to try and lift it up, it's going to swerve to the right, and that has to do with that angular momentum vector, okay, and right-hand rule. I am going to skip section 11.5. You are not responsible for this at all. 11.6, if the net torque on a system is constant, okay, change in angular momentum with respect to time is 0, so angular momentum is 0, so sum of torques is 0. So total angular momentum of a system remains constant if the net external torques acting on the system is 0. Kepler's laws, you're not responsible for this. You can go through it in the text if you want. Okay. Let's take a look at conservation of angular momentum, but as a bullet strikes the edge of a cylinder. Okay. So you have a bullet with lowercase m, so a small mass, moving with some velocity v, and it's going to strike and embed itself in the outer edge of this cylinder that has a mass of uppercase M. The cylinder is initially at rest and begins to rotate about its axis of symmetry, which remains fixed. Assuming there's no friction, what is the angular velocity of the cylinder after the collision, and is kinetic energy conserved? Okay, let's take a look at this. I'm going to go to my whiteboard. Okay, so L is angular momentum, which is R crossed with P. So angular momentum is also R sub O mv. So for the cylinder, my moment of inertia is 1/2 m RO squared. And my moment of inertia of the bullet is m RO squared. So this R is here. Linear momentum P is mass times velocity. So that's how I got this. So this is one moment of inertia for the cylinder. This is the moment of inertia for the bullet. Angular momentum is also moment of inertia times angular velocity. So if we look at this, you have the moment of inertia of the cylinder plus the moment of inertia of the bullet squared. All right, so if we plug this moment of inertia in for the cylinder, we have 1/2 m, the mass of the cylinder, plus the mass of the bullet. So this is after the bullet gets embedded into it. R sub 0 theta times the angular velocity. Well, if I rearrange this to solve for angular velocity, I end up with angular momentum divided by 1/2 the mass of the bullet plus the mass of the cylinder, RO squared. Again, angular momentum up here, I'm going to substitute mvRO for angular momentum, divide this by the 1/2 m plus m, cylinder plus the bullet, RO squared. Well, the RO squared in the numerator and one of these will cancel. So I end up with 1/2 m plus m plus m times r sub 0. So remember this. Now what I'm going to look at is kinetic energy. Kinetic energy in the initial condition and kinetic energy in the final condition. Okay. So I need more space. So if you're looking at kinetic energy in the initial condition and kinetic energy in the final condition, you have 1/2 moment of inertia of the cylinder times angular momentum squared, 1/2 mv squared, right? 1/2 m RO squared, W squared, minus 1/2 mv squared. So now plugging in for my moments of inertia for the cylinder, and I get 1/2 times moment of inertia of the cylinder is m RO squared, angular velocity squared, plus 1/2 m RO squared, angular velocity squared, minus 1/2 mv squared. So continuing on with the algebra, delta K, change in kinetic energy, mass of the bullet, mass of the cylinder, 2 times the mass of the bullet plus 4 times the mass of the cylinder plus 4 times the mass of the bullet, v squared. This is delta K. So KF, K final, is actually less than K initial. So kinetic energy in the final condition is less. Why is that? Well, it's an inelastic collision, so there's some thermal energy that's getting converted when that happens. But total angular momentum is conserved. Okay. Total angular momentum is conserved, but kinetic energy is not conserved. Okay. So you have a spinning top will precess around its point of contact with a surface due to a torque created by gravity when its axis of rotation is not vertical. So spinning tops, gyroscopes, this stuff, this is not going to be on the test. You're not responsible for it, but some of it's kind of interesting. Angular velocity of this precession is given by that equation. This is also the angular velocity of a precession of a gyroscope as it is shown. So gyroscopes are used on ships for navigation. Inertial reference frame is one in which Newton's law holds. A rotational reference frame is non-inertial, and objects viewed from such a frame may move without a force acting on them. So there is an apparent outward force on objects in rotating reference frames. This is a fictitious force called a pseudo force. The centrifugal force is this type of force. There is no outward force when viewed from the inertial reference frame. Coriolis effect. Okay, so Coriolis effect, if an object is moving in a non-inertial frame, there's a pseudo force acting on it as the tangential speed does not increase while the object moves further from the axis of rotation, results in something called like a sideways drift. The Coriolis effect is what is responsible for the rotation of air masses and low pressure areas in different parts of the world. In the northern hemisphere, they are counterclockwise. In the southern hemisphere, they are clockwise. Now, this is for things like hurricanes, weather patterns, things like that. So when you see during hurricane season, hurricanes coming up, from the ocean, here in North America, they are going to be spinning counterclockwise. You will hear urban legend and myth talking about, well, when you let the water out of a bathtub in Australia, it goes one way, and in the United States, it goes, no. That has nothing to do with the Coriolis effect. The Coriolis effect has to do with much larger, like, weather systems, okay? Angular momentum of a rigid object, L, is given by the moment of inertia of that object multiplied by the angular velocity of that object. Sum of torques is equal to the change in angular momentum with respect to time. Angular momentum is also conserved. Torque is equal to R crossed with F. Angular momentum of a particle is given by R crossed with P. Net torque is change in torque is equal to change in angular momentum with respect to time. If the net torque is 0, the vector angular momentum is conserved. And that is the end of chapter 11. There are problems, sample and recommended homework problems to get you prepped for the test. If you have any questions, come to the Zoom meeting with those questions. Be prepared to ask them. Chapter 12 is next, and have a good night.